cost. And that's been that way since I first picked up a tamper going on 20 years ago. Now, I've also been working on it since then, and we've done, we're on our third generation of original forma designs, endless refinements to the process, a whole lot of experimentation. We've made some good progress up to this point. There's still a lot to do. Go ahead and switch it. Luckily, I'm not the smartest person working on this. David Easton, who most of you probably recognize the name, is probably the person most responsible for bringing rammed earth into public awareness in this country, at least. He cites cost as the primary reason for focusing his energies these days on his new company, Watershed Materials. And what they do is build earthen blocks that are the same shape, size, and strength as concrete blocks. These can be set by any mason with very minimal training. Essentially, it's a different mortar mix that they use, and so it has the potential to really lower cost, and also to use it in institutional settings where render just hasn't been tested yet. The sort of another approach to that to the modular concept is a gentleman by the name of Martin Rausch. If you're not familiar with his work, do yourself a favor and get that way. He's been at this for at least as long as David Easton, I believe, and the man's imagination knows no boundaries, it seems. He recently collaborated on what is the largest rammed earth structure in Europe. It's the herb processing facility for the people who make Ricola cough drops. And at 133 meters long, 35 meters wide, and 11 meters tall, this thing is a monster. And yet, there were no walls tamped on site, no forms were ever set on site. Instead, these large panels, some of them weighing up to 7 tons, were prefabricated at a nearby warehouse, trucked to the site and set one at a time by crane. Interestingly, those panels, as big as they are, use no stabilizer. Well, I take that back. They didn't use stabilizers in the conventional sense, and that's something that some of David Easton's watershed blocks also don't use stabilizers, or don't use them in a conventional sense. But the key thing that these two approaches have in common is modularity. And their success got us to thinking, us being Tierra, got us to thinking about committing to a concept that we've been kicking around for years. Most of the cost in rammed earth, you probably know, is tied up in labor. And a thorough analysis of time on task convinced us that there were real possibilities for savings if we were to add modular options or sort of compartmentalize the tasks. When these projects came along, we investigated a little further, and we found that not only was that true, but we could save money on mobilization costs and equipment costs, that there were real savings to be made in scheduling and crew sizing, that even material costs, which surprised us. And I'll get into that a little more in a second, but we were only interested in doing any of that if we could preserve the sort of traditional aesthetic appeal and the performance benefits of rammed earth. What evolved from that thinking was a system that it works. It's highly adaptable. It can look and function like traditional rammed earth, but it also expands the design possibilities quite a bit. We integrated hardware from across a pretty diverse field of construction industries with everything that we knew about forming and tamping, and we've been able to come up with a system that pretty much blew away our expectations about savings that were possible. I should point out at this right here, I should point out that none of this has been proven in an actual structure yet. We've prototyped the forms, we've prototyped the placement devices, we've done a lot of work on metered mortar charges and all the support systems. We've made the blocks and lifted the blocks, tested the blocks, but in investment in a large-scale project, we're funding this as we go, so that'll be either we have a project where it works on, or we fund it through our conventional rammed earth, which we have no intention of giving up on. At its core, it's, well, we look kind of like Legos here. You have to imagine this is like, this high and 8 feet long. And at the core, though, it's a system of large blocks or panels. They're compacted at ground level, and they're placed with a modified telehandler. We use reusable steel pallets. We use reusable steel formwork. They're all precision machined so that we can get ease of assembly and the kind of tolerances that you need in the finished project, and be able to repeat it without because the idea is that one of the ways it's more flexible is that we don't have to, the way we do now, we have to wait for the foundation to be poured, and then the rammed earth crews move in. And we can spend a great deal of time on a project holding up everything else that's going on with the construction until we get out of there. So, the schedule is dependent upon the skill of the rammed earth crew. This new system we could be doing while either during the planning phases, once the design and development had been finalized, but while the foundation was being prepared, we could have the blocks ready to go, or we can mobilize them on site, whichever one makes most sense for that particular project. We can do radius sections, we can do tapered sections, curved sections, corner blocks, we can do them with or without indexing features, with or without voids for reinforcement. The forms themselves are extremely modular. They assemble and disassemble in a matter of minutes, and there's really the only limitation. We even have made them. We've made slots for form liners so that we can easily put texture on some or all of the surfaces, and we've made everything compatible with the forming system that we already have, so that they can be combined with we can combine them with either with monolithic sections or with conventional materials. Those problems we solved a long time ago with our existing forming system. I apologize for having to read, but I'm not all that good at this. I wanted to say that within limits also, we developed this metered mortar gun, say that 4 times fast, metered mortar gun, where we can dial in a specific charge. And what that lets us do is using basically voids on the bottom of the block and the right meter, we can create a dry stack look, we can use conventional mortar joints, or within limits, we can sort of, what would be the word? We can blend the joints to make it look like a monolithic wall within limits. We're limited to about an 8-foot width at current time, just because the block size that we're able to lift is going to be about 4,000 pounds, and assuming certain wall thicknesses, we just run into physics problems at that point. Eventually, we may go bigger with it. I don't know though. So initially, this was just an exercise in cost savings, but the more we got into it, the more I realized what a powerful tool modularity could be. If what you're looking for is cutting edge building performance, then this allows us to easily follow the science with regards to things like wall thickness and mixed design. And that would be true whether it's, even if it's a different on, say, a north-facing wall than on an east-facing wall. If creative expression is your primary goal, it kind of opens up a whole new box of crayons. And where cost is a concern, we happen to think that it's a beautiful material, and given that, a few simple block forms arranged in an elegant composition might be considered a bonus if compared to other structures in a similar price range, and the price points we've done case studies down, or done design studies down to, go pretty darn low. We can do this stuff for close to low income levels, certainly for affordable income housing. So where the savings are, labor, obviously, the forming times are cut by 2/3. We can, and that's just the amount of square feet that we can form during a given man hour. We've cut that down by well, we can do it in 10 hours what it used to take 36 hours to do. So a little less than a third. Same is true of the stripping times. The mixing, we do it in much smaller batches than we would for when you're mixing. Weird things happen when you're ramming earth in big forms. Okay, you want to mix enough to be able to get a couple of lifts in. Otherwise, all you're doing is going back and forth, climbing in and out of forms all day long. So you want it to be able to mix enough to get it in there, but the stabilizers give you a very limited shelf life. Once Portland is hit by water in the mixing pile, you've got so many minutes to get it wet, to get it mixed, and get it into the forms. This takes a lot of the pressure off that, so there's not a lot of lost time. Say 4:30 rolls around or 4 o'clock rolls around, you really have to think twice about whether you're going to try to do 4 more lifts on a big form. With this, that's not the case. You can kind of just keep it going using smaller mixers and smaller placement, and get it in and get it done. And your days are not limited by the amount of time you're looking forward on this task. The other thing is, when you are camping, you are standing outside the forms. That is such a huge plus. We spend literally half of our day climbing up and down inside the forms, and it's not just once in and once out for every time. When a mix is finished, the guy comes out of the tamper. We're over there, we're mixing. By then, hopefully we have, we have another mix, another batch ready to go. We bring it up, it goes, first of all, someone goes in and does a top to form measurement to the compacted earth all the way around, and you've got to do that all the way around. It comes out, the earth goes in. You're either risking your crew or you're getting them out of the forms when you're dumping the earth into the forms. And then everybody goes back in, the dirt has to be redistributed, another measurement is taken from the top of the forms to the loose compacted earth to make sure you've not got too much earth in there. At that point, you can lower the tampers in and start tamping. Now you're trying to get 3 lifts tamped in less than, say, 35 minutes. So people are just like hopping, and that tends to lead to either you slow it down intentionally and only do 2 lifts a batch, or you make mistakes and end up tearing stuff up. Neither one of those is a particularly good option. So that is where the majority of the savings come from. The mobilization costs are real. We don't use near as much equipment in this system. The scheduling cost, that goes back to things like rain days and stuff, where if the blocks and stuff are being made in an enclosed environment, we don't lose time to drying out piles. We don't lose time that we can't tamp because it's raining. We don't lose time that we can't tamp because it might rain. If you get a wall up and then you get 6 inches of rain, well, the first 2 lifts are fried. So, okay, so that's that. Okay, the last thing I want to talk about is stabilizers. When I say we can save on materials, we can. We can do thinner wall sections with this than we can with traditional rammed earth. That means less material. That's not really a major cost, but stabilizers can be, okay? The stabilizers that we're using in this industry right now are either Portland cement most of the time or lime. As a movement, we kind of give lime a pass, and let me explain what I mean by that. The carbon costs associated with the mining and milling of limestone for both Portland and lime are essentially the same. A lot of times it's the same rock from the same quarry, same pile shipped to 2 different places. Portland takes a beating after that because of the high temperatures and length of time it takes to fire it or calcine it, which is the technical term. Lime uses less energy, but we do cook it at 1800 degrees for 4 hours, which ain't, it's nothing to sneeze at. At that point, Portland is essentially ready to package and ship. Lime has to be slaked. That involves a great deal of steam under a lot of pressure. If everything was equal from that point out, then the math would be easy enough to do. But there are a grand total of 5 lime kilns in Texas, one of which produces strictly for the food service and agriculture industries. Of the remaining 4, 2 of them are within a few miles of each other and share one distribution hub. If you drove from Marble Falls to New Braunfels in a straight line, you could see them both. So that leaves us with 3. By contrast, there are 3 cement kilns in the greater San Antonio area alone. So carbon costs matter. Then there's the oft repeated theory that lime will absorb in carbon what it takes to produce it. This is at best, at very best, a hypothetical possibility. In reality, the distance between the lime-air interface and the carbonation front, which is an easily identifiable point at which reabsorption either slows to a crawl or halts altogether, is measured in millimeters. That's the reason why the thickness of a lime render, lime plaster, matters so much. Okay? So any lime beyond the point at which it can reabsorb has limited cementitious potential, not near as much as Portland does, but it does have some. But its carbon costs of its production are left unmitigated by any reabsorption. Now, all that said, I'm a big fan of lime, and here's why. Because years ago we tried this, we had an idea for reducing the amount of stabilizers, and we had to abandon it for constructability reasons. But as we were developing this new modular system, it kind of forced its way back on the table, and I know I'm running out of time, so let me hurry. What is it? It's essentially, it's an old technique. It has competing origins. I like the Spanish claim, not because it's a better one, but because I like their word for it. They call it calicastrado, which is just a lot of fun to say. And basically, it's putting the lime or putting your stabilizers where they do the most good. Let me show you how that works. These are really simple graphics. I have dumbed them down intentionally. That is not for your benefit. That is for mine. Okay. So we got our basic form here with the end cut off for visibility. Go ahead. We throw in a few compacted layers, again, for clarity. Okay, these we'll imagine are compacted lifts. These gradations here are exaggerated, and hopefully the reason for them will become obvious soon enough. We have another piece of apparatus. It's a steel coffer, and it's also the end cut off for visibility. And it's just a thin piece of steep metal with standoffs. It fits inside the lime, inside the form. It goes in and out easily, but doesn't have a lot of play. We drop that in. We fill the outer perimeter of the form with a lime-rich soil, say 8%. We fill the inner side with a lime-poor material, basically unstabilized. And by modifying our then we pull the coffer. By modifying our compaction patterns, we can essentially get the surface erosion, the surface durability benefits of an 8% stabilization using less than 1.5% lime. And that is a neat trick. Now, those numbers will change a little with the geometry of the block, but all things considered, it is a good number. So, I guess that's about it, time-wise. Except I will say this: the best place to save money in rammed earth construction is on your drawing boards. If you get to know the material, really know the material, or work early with someone who does. And I don't just mean the resource and the performance benefits of it. I'm talking about the process. I'm talking about the preparation. I'm talking about its limitations and its